nosotros Size el día de hoy. Espero que estén listos. Yo creo que en unos minutos empezamos. Natalia va a darles la biografía del doctor para que todos estemos enterados de quién es, qué es lo que va a platicarnos el día de hoy. Entonces, en unos minutos empezamos.
Okay, I think we can start now. First of all, thank you for connecting. Thank you, Dr. Rayman, for coming and give us from your time. We're really glad that you're here. And as an introduction for all the invitees, Dr. Rayman is the JPL's Chief Engineer for the Mission Operations and Science. He combined his scientific training with his lifelong study and passion for astronomy and exploration of space by joining JPL in 1986. His work there has spanned a broad range, including optical interferometry, missions to detect planets and around the stars, design of a mission to return samples from Mars, a laser altimeter for Mars, the Spitzer infrared space telescope, the development of the systems to use lasers instead of radios to communicate with interplanetary spacecraft, and more. Marc was the chief engineer of the Dawn mission, which visited 2 worlds in the asteroid belt, Vesta and Ceres. So thank you so much, Dr. Rayman, for joining. And yeah, I'll let you give us all the knowledge you can. Thank you.
Well, thank you for having me. I really appreciate Bruce having invited me and all of you joining me here. But actually, before I get started, Bruce, did you want to say something about your book or something, or should I just jump into my stuff here?
Yeah, maybe just very, very briefly. In November of 2018, I had the opportunity to visit JPL for a full day. It was like a promotional part of our work with our book about Costa Ricans and NASA, and got a chance to meet a couple of them. But one of the greatest highlights of all was actually meeting Dr. Rayman here. And it was at like the last day, I think, the second last day of the Dawn mission, just when they were actually turning the spacecraft off. After how many years had you worked on that?
More than 11. Well, we had flown it for more than 11, and I'd worked on it for 16 years.
So it was a really interesting moment. So yeah, I just wanted to mention that personal anecdote. I'm thrilled to see you again, and thanks again for being part of this.
Well, again, it's my pleasure. And I'll tell you, I've been a space enthusiast my whole life. Literally, I became interested in space when I was 4 years old. And I decided when I was 9 that I wanted to get a PhD in physics and work for NASA. But it was a few more years before I did. And to me, seriously, I feel like I'm living a dream come true working at JPL and getting to do the things I do. And I just love it. I mean, I'm as passionate now about it as I've ever been. It's so exciting. I can't get over how lucky I am. So I have a few slides to show you. It's not a formal presentation. These are just, people asked me to just show some things about my favorite missions. So I'm going to show you some stuff from my 2 favorite missions, just a little bit about it. But I hope that mostly what we could do here is just talk about stuff. You people have things you're interested in, questions you want to ask. I'm interested in hearing what you're interested in talking about. And as we were talking about before you joined, you can ask anything you want. I allow myself to tell you that I don't know the answer. So, I'm going to share my screen here when you allow me to. We need to redo you cannot start screen share while the other participant is sharing. So again, when I can show these slides.
Can you try again? I'm sorry.
Okay.
Okay.
So can somebody just confirm that you can see this? Okay.
Yep.
See Martha's
Yep.
thumb up. That's what I needed. Thank you, Martha. So again, I'm just going to sort of tell you some things that I think are kind of fun about some of these missions I've worked on. In particular, Dawn, which is the spacecraft that you see going through the center there, which went to Ceres in the upper left and Vesta in the lower right. I should also clarify, maybe this is the same for you, but I'm doing this from my house because of COVID-19. I can't go to JPL. I haven't been there in 3.5 months, actually, I guess 4 months. And so I hope my home internet connection is good enough to be sending this decent quality. If it turns out to be jerky at some point, don't worry about it because I'm not going to show you anything that will be problematic. But anyway, you already heard in the nice introduction from Natalia that Dawn visited Ceres in the upper left and Vesta in the lower right. So I'll tell you a little bit about that. And another mission that's a favorite of mine, Deep Space One, down at the bottom, which went to Comet Borrelli. But as I mentioned, I've been interested in space my whole life. And when I was 11 years old, I had saved up my money and I bought a little telescope. And I spent 2 or 3 nights a week outside in my parents' yard. We lived in a small town near a woods. And so it was nice and dark. And I could look up at the night sky. And that's what I spent most of my time doing. And it never occurred to me that there might be something in the sky like that, that when I grew up, I would be responsible for exploring. So this is Vesta, which is the second largest object in the main asteroid belt between Mars and Jupiter. And until the Dawn mission, this was the best view we had of Vesta. And this was from the Hubble Space Telescope. But when Dawn got there, it turned it into a much more detailed view. And to me, one of the things that is so cool about space exploration is literally getting to explore alien worlds and to take an object like that, that for 2 centuries, Vesta was discovered in 1807. Dawn got there in 2011. So for 2 centuries, it was little more than just this faint smudge of light amidst the stars. And now you can see Dawn turned it into this richly detailed, complex view of an alien world. And I mean, again, what could be cooler than that? And here's just a close-up, just one of the, Dawn took 30,000 pictures. Unfortunately, Bruce and Natalia and others didn't allow me enough time today to show you each and every individual picture. So I'm just showing you one that's one of my favorites that shows these 3 craters here that we call the Snowman. You don't get a lot of snow maybe where you are, but you undoubtedly know what a snowman looks like. And just for scale, this crater here is around 70 or so kilometers in diameter, a little more than 40 miles. And one of the things you can see here is that the area up here, can you see my cursor? Can Martha, you give me a thumb? Thank you. This is very densely cratered. And here, there are very few craters. The reason for that is actually, if I go back to my, I guess I can't easily go back to, let's see. Okay, well, I'll leave it here. There was an impact on Vesta that we believe was about 1 billion years ago that was so powerful, it ejected a tremendous amount of material and resurfaced most of the southern hemisphere. And so the craters that had been there before were covered over and erased. And so that's why this part of Vesta looks smooth. But the material that was blown out from this impact and settled on Vesta didn't get as far as up here. And so that's why it's very densely cratered here. So I think this picture captures a lot of cool things, showing all the detail we could see in this crater and the generally more densely cratered ancient terrain in the north and the more lightly cratered southern terrain in the south. So I just think that's kind of a fun picture. I'm not going to take the time to tell you a lot about Vesta. Just wanted to show you that. Now I want to go on to Dwarf Planet Ceres, which you can see here, put together with pictures from dawn. And you can see there are bright areas, there are a lot of craters, there are these rays like here. But the main thing is bright things like that. And this is that crater, which is 92 kilometers or about 57 miles in diameter. And in the center of it, this amazingly bright material. And tell you, when Dawn first started returning pictures like this, as the spacecraft flew closer and closer and closer to Ceres, we started seeing this bright stuff here. And some people asked us, could this be the lights of an alien civilization? And you know, when you hear questions like that, I find questions like that really disturbing. I mean, here we're taking the best of humankind, science and technology, combined with our most noble spirit of adventure, creativity, discipline, in order to accomplish a mission like this. And yet people are asking, could this be the inhabitants of Ceres, Syrians, and their lights in in this extraterrestrial city? I feel like, whatever happened to critical thinking? Why can't people be more disciplined? Because after all, how do we know if the Syrians live in cities? Maybe they live underground and the lights of their cities don't escape. Maybe they live in more rural communities and they don't have distributed lights like this. So how could you know? But anyway, what this really, to me, makes you want to do is fly in closer for a better look. And that's exactly what we did. And what we now understand is that this area here, which is around 10 kilometers or so across, a little more than 6 miles, is actually a result of there being underground salt water at Ceres. In fact, we now know that at one time in the ancient past, the distant past, Ceres likely was covered with a global ocean of liquid water. And that water has long since, billions of years ago, it froze and was blasted off by impacts from other objects. But some of the water still persists underground. And some of it makes its way to the surface, as it did in this crater, and then it freezes in the cold vacuum of space there, and then it sublimates. That is, it transforms, goes from being a solid to a gas. So the water molecules just dissipate, but they leave behind the salts that were dissolved in them. And the salts are much more reflective, they're brighter. And so what you're seeing here is bright salt deposits left over after underground salt water made its way to the surface, sublimated, and just left the salts behind. So I think that's a really, really remarkable discovery there. And here is a view Dawn took from a much higher altitude. And you can see here on the limb, this bump, and it turns out, we get in closer, this is the tallest mountain on Ceres. From these plains here to the summit is about 4,000 meters. I presume most of you are comfortable with metric units, right? Okay, good. Excuse me. So it's about 4,000 meters high. That's pretty nice mountain. And we now understand that it's an ancient volcano. So Ceres, because Ceres is farther from the sun than Earth, so it's much colder, but it still has active geological processes like Earth does. And on Earth, volcanoes erupt with magma. On Ceres, this cryo, as in cold, cryovolcano erupts with what we call cryomagma, which is a mixture of that underground water and salt and rock. So collectively, you could call that mud, came up onto the surface, and it formed this amazing structure here. And here's another view of it from within that nearby crater. And now you can really see what a distinct, sharp structure is. Here's the ground, and boom, all of a sudden it goes up. You can also see these streaks, like here, of bright material, which is some of the material that had erupted from the summit and flowed down the surface. I should also mention that from the low point of this crater to the summit is only, in vertical distance, is only, I can't remember, it's only around 17 kilometers or something like that. And while it's from the bottom of the crater to the summit is a vertical elevation difference of around, I don't know, 6, 7, 8,000 meters. The gravity on Ceres is only a 40th of what it is here on Earth. So I think a good activity would be for all of you who are interested in space to organize a nice day hike there. And if you organize that, I will join you. And collectively, we can just wear our spacesuits and have a nice hike from the bottom of that crater to the summit of that cryovolcano. I think it might be a fun thing to do sometime. Anyway, that's just another cool place on Ceres. And I want to show you one more. This is the wall here. This is the wall of a crater. And here's the floor of the crater. And this crater is, we estimate, 1 billion years old. But I want to highlight a few things for you. Like, I don't know how well you can see it, but there's a trail of small craters there. And at the end of that trail, there's the rock. So what we're seeing here is a rock that tumbled down this crater wall. And as it bounced its way down, it left all those impressions. And dawn got so close to Ceres that we could even see that rock at the base of the trail. And you can see many more of those. There's another trail, and there's the rock at the base. And you can see more in different places, and you can trace each one of them back. And again, I'll tell you, just in all honesty, I think it is so cool that we could send a spacecraft to a dwarf planet between Mars and Jupiter and get so close to it that we could get these amazing views. And in fact, in its final orbit, dawn was only 3 times higher above the ground than people are who just fly in a commercial aircraft. It got to altitudes of less than 35 kilometers. That is, I think, amazing for a dwarf planet so far away, for a spacecraft at a dwarf planet. I'll also point out up here on the crater wall are more objects that are stuck in basically stuck in the dirt. But sometime, whether it's because of internal geological activity, basically the equivalent of earthquakes, you could call them Ceres quakes, or maybe because an object will slam into Ceres, something from the asteroid belt, and shake it. Eventually, those will give way as well. They'll become loose, and they'll fall down and create still more of these tracks like what I've shown you. So I just think that's cool and wanted to share that with you. But I also want to talk about the size of these objects. So this is Vesta as photographed by Dawn, and all of the other things that people normally call asteroids that have been visited by spacecraft. And in that box at the bottom, if you look carefully, you can see there are objects in there. I really did include them. I'm not trying to cheat you here, but maybe you've heard of Osiris-Rex, which is at the asteroid Bennu. Many people mispronounce it as Bennu, but it's Bennu. Maybe you've heard about so that's a NASA mission. Maybe you've heard about the JAXA, that's the Japanese Space Exploration Agency, mission Hayabusa 2 at Ryugu. Those objects are interesting, but you can see they're pretty small compared to Vesta. Vesta is well over 500 kilometers in diameter. It's a big place. And if you bring Ceres in, you can see it's even much larger. So I just wanted to give you some context, because even though Vesta and Ceres live in the main asteroid belt, they're not at all like typical asteroids, which is why, again, Ceres is called a dwarf planet, just like Pluto is. Vesta is often called a protoplanet. So here they are again. Vesta already is about around 525 kilometers in diameter at the equator. Ceres is around 940. And once again, you can compare them with the two largest objects that other spacecraft had visited. They're much closer in scale to other things that you can imagine. And excuse me for a moment. So you can get a sense that these are big places. And part of what's so exciting about exploring them is, think of how much area there is in Costa Rica. Excuse me. And yet Vesta has something like 10 times the surface area of Costa Rica. Because of course, Vesta is round, it's a three-dimensional world, so much more area than depicted in a picture like this. And that's what I think is so exciting about exploring these places. So I also wanted to just give you an overview of the mission. We departed from most people's favorite planet, Earth. We launched in 2007. I don't know if you could hear that or not, but thank you, Martha. I threw that in just to help you stay awake during my otherwise boring presentation. And on the way out to the main asteroid belt, Dawn flew by Mars and used it for a gravity boost. Sometimes that's called a gravity assist. Maybe many of you are familiar with that, and I won't take a lot of time to talk about it, but I will point out that the basic idea is, by having the spacecraft fly by another planet, we can extract energy from Mars' orbit around the sun and give it to Dawn in order to help boost it. But of course, we have to conserve energy. So if Mars helps speed Dawn up, then that means Mars has to slow down in order to conserve energy. And Mars actually now goes around the sun more slowly than it did before Dawn flew by in February 2009. And so if you're keeping track, the change in Mars velocity because of Dawn flying by amounts to about 2.5 centimeters in 180 million years. So Mars goes more slowly by that amount because Dawn flew by. Anyway, in July 2011, we got to Vesta, and most of those other objects that I showed you that spacecraft have visited, they just fly by. Dawn actually went into orbit, and as you can see, we spent 14 months there, excuse me, making a comprehensive investigation, then broke out of orbit, flew for another 2.5 years, and around 1.5 billion kilometers to get to Ceres, and went into orbit around it. Got there in March of 2015, And Dawn is there now and will be there for all intents and purposes forever. And at each destination, you can see we made a comprehensive set of investigations. And I won't take the time here to talk to you about all of them, but rather show you that by being in orbit, instead of doing a flyby, again, a brief visit, which is what many spacecraft do, Dawn orbited these objects. So this chart illustrates some kind of interesting things. Dawn is the only spacecraft ever to orbit an object in the main asteroid belt. It's also the only spacecraft ever to orbit a dwarf planet, in addition to being the first one to reach a dwarf planet. But to me, most impressive of all is it's the only spacecraft ever in more than 60 years of space exploration to orbit any two extraterrestrial destinations. Which, when you think about it, is very surprising. It seems like an obvious kind of mission to undertake. Go to one destination, do whatever you're going to do there, and then go to another and do the same thing. And yet it had never even been tried before Dawn. And the reason for that is that prior to Dawn, we didn't have ion propulsion. And that's what really makes this work. And I should say much prior to Dawn, we didn't. And this is, I hope you recognize in the center, the Star Wars TIE fighter that Darth Vader and others in the evil empire used to fight Luke Skywalker and others in the Rebel Alliance. And in the Star Wars universe, the TIE fighter, TIE, stands for Twin Ion Engine, because that was the most futuristic, coolest, advanced technology that the makers of Star Wars could think of. And to me, one of the rewards of working on a project like this is getting to turn that science fiction into science fact. And here's Dawn using one of its 3 ion engines. So we do the Star Wars TIE fighters one better, as it flew into orbit around Dwarf Planet Ceres, excuse me, just a few years ago. And this is a photograph of an ion engine operating in a vacuum chamber at JPL, where I work. And you can see it really does produce this cool blue glow like in science fiction movies. And the reason for that is we use the propellant xenon, which is like helium or neon, but heavier. And xenon just happens to glow blue, just like neon and neon signs happens to glow orange. And this ion propulsion system has 10 times the efficiency of conventional chemical propulsion. So just imagine how much more effective an automobile would be if it had 10 times the mileage, if it could go 10 times as far with the same amount of gas. And that's what allows us to undertake missions that are much, much more ambitious, or in this case, impossible. Dawn would be impossible without ion propulsion. And here's a video, I hope it comes through with my internet connection and yours, of Dawn, thank you, Martha, Dawn firing up its ion engine. And although the thrust is very efficient, it's also very, very gentle. And so we thrust for very long periods of time. And that's what Dawn looked like for much of its interplanetary flight. In fact, excuse me, we used Dawn's ion engine to thrust for a total of years, almost 6 years of Dawn's time and space was spent thrusting with its ion engine. And that allowed it to change its own velocity over the course of its mission by around 11,500 meters per second. That's uniquely high. No spacecraft has ever been able to do anything even remotely like that. In fact, just to get from the surface of Earth to low Earth orbit takes much less velocity than that. And as you know, when you saw things like the space shuttle take off or the Falcon launch vehicle that recently sent astronauts to the International Space Station. Those launch vehicles, those rockets, could not change the velocity by nearly as much as Dawn did just with its ion engine. And once again, that's what makes a mission like this possible. So here's a view of the spacecraft when it was being built in a clean room. And here's another view. I like this view because this is one of the two solar array wings. Here's the main antenna here. For scale, it's about 1.5 meters in diameter. There's my friend Tom. Here are some of the instruments that we use to study Vesta and Ceres. But this one solar array is 8.3 meters long. And of course, we have two of them. And the reason we have such big solar arrays is because the spacecraft goes far from the sun out to Ceres 3 times the Earth's distance from the sun. So sunlight is weak. So you need a large area of solar cells to capture enough light to produce electrical power to run the ion engine and the other systems. And as you may know, one of the most stressful things about a rocket scientist's career is you spend years and years and years working on these things. You put it on top of a rocket and you hope you have a successful launch. And we did. We had a very beautiful launch, I think. We even launched dawn at dawn. You can see the sun rising in the background here. And we launched from Cape Canaveral, where most of these missions go. And now I'll just quickly show you Dawn's interplanetary journey. This is a conventional view of the solar system. Here's the sun in the center. This is Earth's orbit. So here's where Earth was when we launched. And as I follow along with Dawn's trajectory, if you care, it's fine if you don't, when it's this nice ion engine blue, that's when we were thrusting, and when it's dark, we were coasted. So by the way, we passed the orbit of the moon the day after we launched. So this doesn't have anything to do with, these things in the Earth-Moon system. We had the moon in our rear view mirror very quickly. But we coasted for a while, so we checked out the spacecraft, did some tests with the ion propulsion system and some other tests, but then quickly got into a pattern of thrusting most of the time. And I should tell you, as a technical detail, the software, this is not a joke, the software that generated this plot, for technical reasons I could tell you, it doesn't matter, it exaggerates the duration of these coast periods. If we coasted even for a few minutes, then it would make it look like it was a full day, because this software is only plotting each day, did we thrust or was there any coasting? So anytime you see a short coast period like this, it could be that we coasted just for a matter of a couple of hours or even less. It makes it look like we coasted longer than we did. That's a detail. You can see we use the ion engine to spiral farther and farther away from the sun. There's a long coast period during which we flew by Mars, but then we resume thrusting, leave Mars well behind, push out farther and farther and farther until we get out to Vesta in July of 2011. Then we did a lot of thrusting in orbit around Vesta. That's not depicted in this plot, but we stayed with Vesta as Vesta orbited the sun. Then in September of 2012, fire up that ion engine again and climb for another 2.5 years and 1.5 billion kilometers of interplanetary travel till we get to Ceres, go into orbit around it, and then we stayed with Ceres for years as Ceres continued its own trajectory around the sun until the mission came to an end, although Dawn will stay in orbit essentially indefinitely. So that's just a quick overview of Dawn. But I also want to show you this other mission, and I won't spend nearly as long on this. I think we want to move along. But it was called Deep Space One, and this was before Dawn. And I have a personal affection for this mission. I really love some of the things it did. And part of its objective was to test 12 astounding technologies on an operational interplanetary mission, one of which was ion propulsion. And this was the world's first interplanetary mission to use ion propulsion. And this is what made Dawn possible, but other missions as well. And you've perhaps heard of the 2 Hayabusa missions from JAXA that use ion propulsion. Maybe you know about the European Space Agency's SMART 1 and Bepi Colombo missions that use ion propulsion. But Deep Space One was the first. And that was the first mission where I was responsible for the entire mission, which is part of the reason I have so much affection for it. And we tested also some technologies in autonomy and artificial intelligence. And I know some of you are interested in software and advanced machine learning and things like that. Deep Space One was the first one to use artificial intelligence systems in space. And it's obligatory, there's a requirement, you always have to show a photograph of the spacecraft, so there it is on the left. And of course, we all like rockets because they make a lot of noise and they're big and they're cool. But of course, the rocket, for all of these missions, while important, represents, the first few tens of minutes or hour of a mission, and the rocket doesn't take you very far. But I wanted also to show you my favorite photograph of Deep Space One. I hope you'll indulge my personal preference here. And that is here. And there is Deep Space One. This picture was taken when Deep Space One was 9 times farther away than the moon. This was taken with the 5 meter, maybe you've heard of it, there's a well-known in the astronomical community, 5 meter or 200-inch diameter telescope called the Hale Telescope on Palomar Mountain in Southern California. And when it took this picture, I know some of you may know about astronomy, some of you don't. This star here is 10th magnitude, which means it's much, much too faint for you to see with your unaided eye. And Deep Space One here was visual magnitude 22.5, which means it's about 4 million times fainter than you can see with your unaided eye. And as you also know, when big telescopes, or even some small telescopes, take pictures of the stars, the telescope has to move to compensate for Earth's rotation, right? So you don't get a smeared image. I hope that makes sense for long exposures. But so the telescope moved to keep the stars as point-like objects. They're a little smeared out. This doesn't tell you anything about Deep Space One's shape, but rather, during the long exposure, DS1 had its own independent motion through the solar system. And so part of what I like is this picture says to me, we have a spacecraft out among the stars. And of course, it's not really as far away as the stars, but it was much farther away than the moon. And ultimately, Deep Space One and Dawn got to fantastically large distances, more than 1,000 times the distance to the moon, more than 1 million times as far as astronauts on the International Space Station. And I think that is really profound and exciting that humankind, and I don't mean just me, I don't mean just the people at JPL or at NASA, I mean all of us, people like you, who I think everyone who's ever looked up at the night sky in wonder, anyone who's ever had just that burning passion for a bold adventure far from home participates in missions like this. And that to me is what's most exciting about these kinds of missions. But I also just want to tell you that Deep Space One went on and got NASA's first close-up pictures of the nucleus of a comet. No spacecraft had ever done that before. This is Comet Borrelly, and here, when you look at it from different views, you can see it's not a straight object, it's bent, which I think is very interesting. And here, where we intentionally overexpose the nucleus of the comet to show these jets of gas and dust shooting off here and here. You can even see a little one here. It gets bright at the end because there was a sort of an eruption of gas as Deep Space One, excuse me, was visiting it and taking these pictures. So I also think that's kind of neat. And there's just another view of it where we have used color to encode the density of the dust around this comet. So for reference, this is about 8 kilometers or so across like this. But you can see it's got this enormous jet of dust and gas. And it was actually in a cloud of a still larger cloud of dust and gas, but I'm not showing you here. There was many thousands of kilometers across. So it was very challenging for Deep Space One to go into that cloud and get these images. And I will conclude with just a quick view of DS1's trajectory. Here's where Earth was when we launched. Again, more coasting and thrusting. This was generated with different software, so I won't bore you with the details of it. We flew by an asteroid in 1999, had an exceedingly serious problem here, and Bruce and others have access to a video if you're interested in hearing about truly one of the most amazing interplanetary rescues of all time. When Deep Space One was farther away than the sun, it had this dramatic problem because when DS1 was here, Earth was up here, farther away than the sun, had this awful problem. It should have been a catastrophe, but we managed to conduct this interplanetary rescue, excuse me, during which DS1 coasted all the way around or halfway around the sun till we rescued it here, then fired up the ion engine again, headed off for this long interplanetary journey of 15 months and well over 1 billion kilometers to get to Borelli and get this picture. So if you're interested in more about that, could give you a link to a YouTube video. But that's pretty much what I wanted to show you. Some things that, again, were part of my luck. I mean, I've had, truly, I'm very serious about this. I'm very lucky to be able to work on missions like this. I don't believe in destiny, and I don't believe that, you know, that people can do it only because they have passion and dedication. I think that's an important part of it. But part of it is just luck as well. And I like to acknowledge the fact that I had luck in being able to accomplish what I did. But I think another aspect of my luck is that I get to share it with people like you who also love some aspect. Each of you is different, but you each love some aspect of science or engineering. And you, like me, like to look up at the sky and think about how exciting it is to be able to send spacecraft there and explore it and learn more about it. And so part of my luck is to be able to get to have this event with you.
Marc,
and I apologize if I took more time than I should have.
Oh no, thanks a lot. I think we're all amazed, and it was such a great experience to see everything. We have a lot of questions as expected. So let's start. I also want to tell the people that you can, I'll tell that in Spanish. Todos pueden preguntar en el chat de el Zoom, pero también pueden levantar su mano si desean hablar y hacer las preguntas directamente. Entonces, también pueden levantar su mano y Natalia les va a dar el permiso. Entonces, vamos a empezar con las preguntas. Van a ser en inglés y we will start with the questions now.
Okay, can I just say one more thing?
Sure.
And that is, I apologize to you for giving my presentation in English. I regret that I'm not fluent in another language. It's seriously a lifelong regret of mine. I wish I were, and I admire people who are multilingual. I wish I were. Anyway, go ahead.
No, don't worry. I mean, it was great. I think we know a lot of English, and if not, we can translate. So the good thing is that we can all learn.
Good.
One little interjection from me. I promise not to ask all the questions, but there's an interesting little fact. Two Costa Ricans helped build Dawn at some point. I can't specify when it was, but I put a couple of articles in the chat. Their names were Joseph Mora and Alejandro Mora from San Antonio de Desamparados. So yeah, if you want to read those articles, a little bit of Costa Rican fingerprint on Dawn.
Yeah, cool.
Okay, so let's start. What have we learned as human beings from the origin of life after the visit to Vesta and Ceres?
Okay, that's an interesting question. So a big part of NASA's and the scientific community's, a major scientific objective is, not just by NASA, but by many, many others, is to understand what led to the development of life on Earth. And one of the things that we are learning about is by studying other solar system bodies. Now, we didn't learn anything about the development of life from Vesta. Ceres, however, we haven't yet learned anything, but we have the data that may help us. Ceres seems to have many of the ingredients necessary for life. I already told you that it has water. Ceres has a very, very large inventory of liquid water, Most of it's ice. There may still be some liquid. It's underground. Ceres also has organic materials, that is, chemicals that we understand are important for for life. These are molecules made with carbon. Maybe most of you know what organic chemicals are. So we discovered them on Ceres in large amounts. Ceres also has internal heat. So in order to have life, excuse me, you have to have a source of energy. But I showed you that cryovolcano. I told you it's old, but in geological terms, it's old compared to Bruce and me, but it's not old in geological terms. So Ceres currently has internal heat and geological activity. And so we've identified on Ceres many of the ingredients that are necessary for life. And we hope that by studying them in more detail, we can learn more about the chemistry that so-called prebiotic chemistry, before biotic biology. So that's prebiotic chemistry that on Ceres almost certainly did not lead to the development of life. We don't know for sure. There's a minority, and I should emphasize, a small minority of scientists who believe maybe life could have developed on Ceres. But even if it didn't, we can learn more about this chemistry, which under different conditions here on Earth led to people like you and me.
That's amazing. So the next question is, have you experienced any critical situation in the development of a mission? How they managed to solve it?
Critical, you mean a critical problem?
Yeah.
And when you say the development of mission, do you mean while building it on Earth or just in the overall mission?
I think overall mission. I think that's
okay. Good.
Yeah.
Good, because that's the question I want to answer.
Okay.
so yes, absolutely. Deep Space One, I alluded to, had this catastrophic failure. So this was on the way to this comet, a device. So I don't want to get too technical here, but I think most of you have some science and engineering background, right? Many of you, some of you, one of you, none of you. Okay. All right, so I won't get too technical, but I will, again, encourage, Bruce, I sent you a couple of weeks ago a link to this video. It's on YouTube, where I talk more about this, but it had a critical failure of a device which is responsible for orienting the spacecraft in the zero space. And when it failed, we could not point the main antenna at Earth. We couldn't point the ion engine in the direction we needed in order to send the spacecraft to the comet. We could hardly do anything with it. And this was such a serious failure that NASA headquarters said, it's catastrophic. You should just end the mission here. And that might have been the right thing to do. But I tried to get people to adopt the philosophy that if it isn't impossible, it isn't worth trying. And so we spent 7 months trying to rescue this spacecraft in what, again, NASA later described as the most ambitious deep space rescue mission ever undertaken. In fact, I even have polo shirts and jackets and t-shirts with the Deep Space One rescue team logo on it. And I even won 2 NASA medals for doing this. We were successful. I shouldn't be talking about myself. The point is, we were successful, and this was more stressful, more difficult, more, in some ways, more scary than anything I've ever attempted. And yet it was worth it. Sometimes you have to take risks if you want the big rewards. Excuse me. And this was a really, really difficult experience, but it worked out. It's what allowed us to get these pictures of the comet. And I'll just briefly tell you the other mission I talked about, Dawn, the one I spent more time on, it suffered. So I should tell you, most interplanetary missions do not have critical failures. I'm lucky enough, in an ironic sense, to have been in charge of 2 that did. I've worked on other missions as well, but Dawn also had devices fail that there was no way we could foresee that they would fail. We didn't do a worse job designing Dawn and DS1 than other missions that don't have these things. Most missions work pretty smoothly. Send spacecraft to Mars, we send a lot there. That's actually a pretty easy place to get to, but other places as well. And they don't tend to have these failures. Dawn did as well. It had other devices that failed. There was no good reason that Dawn should have been successful. And yet when we were faced with these failures, we didn't give up. You try. Think, well, you just do the best you can. And yeah, it's scary, it's risky, and it takes the most, you have to be as creative as possible, as diligent, as rigorous. I think these failures show NASA, and again, humankind at its best to overcome these problems and succeed. And I apologize, I tend to give very long answers, but there you go.
Please don't worry. I think we're all enjoying it a lot and getting a lot of information. And we have a lot of these questions, like a lot of people have asked it. What would be your advice for younger generations or your younger self or young engineers?
You mean my advice if you want to go into this kind of thing?
Yes.
Okay. So, as I told you, I've been interested in this my whole life. But I grew up in a very small town in a place you've probably never heard of. And my parents were not well educated. They wanted me to stay in this little town that I grew up in. There were, I don't know about the schools you went to, there were 32 kids when I graduated from high school, when I was 17 or 17, 18, that kind of range. It was a little town. It's called Toledo, Ohio, if it matters. And my parents wanted me to stay there. They wanted me to go to the University of Toledo. And although my dad didn't go to college, but that's where their vision of sort of, if my life, if I achieved the maximum that could be imagined, I would go to the University of Toledo and I would get a job in Toledo. And I'll tell you, there was nothing in Toledo for me. I wanted to go to the stars, right? And so my advice is you don't accept limitations that if people tell you you can't do this. Now look, I should say, if my goal was to be a championship basketball player, I probably couldn't have done that. And although you can't tell in this video, if I wanted to be a world-class sumo wrestler, I probably wouldn't have been able to do that either, if you know what sumo wrestling is. So you have to kind of pick your goals wisely. But still, my advice is you keep trying. You keep trying. You don't let people tell you that you can't do it. Now again, let's be realistic. There are things you can't do, but there are amazing things you can. And when I was a little kid growing up in Toledo, Ohio, I couldn't see how it was possible that I would end up getting a PhD in physics and work for NASA and get to be in charge of, I mean, my goal at some point was just work for NASA. It didn't occur to me that I would be in charge of missions. I mean, how cool is that? You know, and I still, again, it involved a lot of luck, but it also involved a lot of hard work and taking risks and just you push yourself. I also mentioned a couple times that some of these rescues, they were scary. You know, it's not always easy. Sometimes you take a technical risk. Sometimes you take a personal risk, right? Maybe when you apply for a job or if you leave, I mean, let me give you an example that may apply to some of you. You may end up leaving, not necessarily, but you may end up leaving the country that is your home. You grew up there. Your friends and family are there. That's your home. And it's scary to go to another country where maybe you're fluent in the language, maybe you're not entirely comfortable with it. You may not know all the customs. That kind of thing would be very scary. Growing up in the little town that I grew up in, even when I went to a university, I went to Princeton University, maybe you've heard of it, maybe you haven't. That was scary for me. There were a lot of people there. They came from families that had a lot more money than my family did. I felt like an alien there, and it wasn't easy. But you know what? I pushed for it, I did it, and then each time I took the next step and the next step and the next step. And even when I was at JPL, where I work now, and I didn't start out where I am now at the, top of JPL, started out down here, and I couldn't have been happier. But at some point I wanted to progress, and I contacted people who were many levels above me, and that was scary. And I asked them, how can I advance things? So the advice I give is pursue the aspect of your interests that you're most interested in. Maybe it's physics, maybe it's engineering, maybe it's biology, maybe it's chemistry, excuse me, within engineering, maybe it's programming, maybe it's electrical engineering, mechanical, chemical, aerospace. I mean, and I'm not trying to list all the things. There's everything. And I'll tell you even, we have people working at JPL who are lawyers. We have people working at JPL who have backgrounds in business because, right, we spend United States taxpayer money. Maybe you end up doing something in Costa Rica where, I mean, maybe you don't work for NASA, but still, you're spending your government's money. You want to do it responsibly. So you need all kinds of skills, business, law, in addition to all of the technical stuff. I think the best thing is pick what you're most interested in, because you need to be happy with it. Pursue that. Look for your opportunities. Take some chances sometime. And that's my advice for what it's worth.
Marc, just interjecting quickly, and you're referring to so many different jobs. Do you know Viviana Velarde in the human resources department at JPL, Viviana Velarde?
I do not. There are 7,000 people working at JPL, and I know about 6,999 of them, so I guess she's the one I don't know. But it sounds like you know her.
Well, we discovered her, you can't really use that word, became aware of her a couple of months ago. She's from Costa Rica, San Jose, Costa Rica. She's been working in JPL's HR department for about 25 years.
Oh,
so
cool.
Who knew, right?
Yeah. I think that's a perfect example. And HR, human resources. I'm sure she doesn't have a technical background, but she doesn't need it because she gets to make as much contribution to the success of interplanetary missions as the technical people do. You need it all.
I agree. That was extremely inspiring. I know a lot of us are about to cry or have something inside our chest because it was so inspiring. But let's continue with, because we have a lot of questions, and this one's really cool, actually. You talked about hiking on Ceres, the crater mountain, which I personally find extremely cool. Oh, I lost it. Just 1 second. Oh.
Well, if the question is,
I can
when
finish
are we going? I'm not ready to answer that. Anyway, go ahead.
Yeah, exactly. When do we go? What do you think? When would we go? And when would we go there to do sports?
Well, so let's see. It's today's Friday, so I don't think we're going to make it this week.
Okay.
Yeah. Well, Ceres is farther away than Mars, and it's a pretty difficult place to get to. So maybe people will get there. I shouldn't say maybe. I have absolutely no doubt whatsoever that people will get there sometime, but it is unlikely to be within the next generation, because right now we don't even have the capability to send people to Mars, right? So I can't foresee when it will be. It might be while you're still young enough to go, but it's going to be a long way off. But I should say that as humankind expands its presence in the solar system, right, in coming years, we will have people go back to the moon again, then eventually to Mars, and then beyond. Ceres is a very attractive place to go on the way to even more distant destinations because of what I told you earlier. It's got water, it's got organic materials, it's got nice places to hike on your day off while you're there. And so Ceres provides many of the resources that humans will need as they extend their reach farther into the solar system. So it will happen sometime, but I'm not in a position to guess when it will be, but it won't be this month.
I want to hike there, sure. Regarding this, regarding the Snowman 3 craters picture you showed, given the potential explanation of the asymmetry in the small crater distribution on the two sides of the Snowman, which has to do with a fall of an old impact debris or dust, my question is if we have a computer model too. It'd be interesting to see how a fall like that makes such a dramatic boundary.
Yes, it would. So so I agree. That wasn't really a question. I agree, it's interesting. But let me just clarify it a little bit. So what happened is, here's my accurate model of Vesta. See it right here in midair. The impact happened near the South Pole. So it hit the ground, a bunch of stuff sprays out, but then Vesta's gravity pulls some of it back in. Some of it continues to go out. And yes, it just blanketed basically the southern hemisphere of Vesta. And I'm sure there wasn't a super sharp boundary, not as sharp as, you could draw with a fine pen on paper, but most of the material landed in the southern hemisphere. So little landed in the northern hemisphere that it didn't cover the craters. And so that's what was going on there. And there has been computer modeling of this, and undoubtedly there will continue to be more to refine the models to include more complicated aspects of it, excuse me, in order to maybe see if we can figure out what, if here's Vesta, did the object hit it like that, or did it hit it like that? And what's the effect of Vesta's rotation during, as the stuff comes up and then settles down, Vesta's turning. And in fact, we even see some evidence in that crater of what looks like a little bit of a swirl, which maybe that's because Vesta was turning underneath this cloud of debris coming down, right? And some stuff lands early, some stuff, if it lands, if it goes up so high that it lands a few minutes later, Vesta has rotated. So to try to understand things like that. So whoever asked the question, I think demonstrates an insightful understanding of some of the things that would be good to try to understand more. I don't know if I addressed that or.
Yes, thank you. Like I was missing before the model that you actually perfectly made with your hands and showing the 3D event as it happened. Like that makes sense that there will be a boundary. Yes.
Okay, good.
Thank you.
Sure.
The next question is, can you tell us more about the imaging techniques on Dawn? Were you looking for something specific when you looked at those pictures for the first time? Anything that surprised you?
Okay, so that's several questions. The first one was the imaging. You said techniques. Okay, is that asking about the technology of how we take the images, or rather more like the strategy?
I think
it was more about the actual technology. I know you had like 2 cameras on it from what I gathered.
Yep.
But if you think talking about this strategy is actually more interesting, like go ahead.
Well, I'll tell you, I think it's all interesting, so you can't go by me. So I'll try to give a little touch on each one, and maybe I'll count on you, Andrea, or somebody to politely cut me off when I'm going too long. Because again, I've already demonstrated I give very wordy answers. So first of all, yes, we had 2 cameras. They're not all that different from just the camera in your smartphone. So we, I should say the reason we have 2 of them is in case one failed. So one is a primary, one is a backup. We take the picture, it's intrinsically digital. It takes about 1 minute at Dawn's highest data rate to transmit a picture back to Earth. That's not how long it takes the radio signal. That's 1 minute of transmission time. So this is wouldn't be good for, a real-time internet Zoom chat session like this, 1 minute for a still picture. As an aside, it took the radio signal around half an hour to get from Dawn down to Earth. Okay, so that's just a couple words about the technology. I can tell you more about it if you want. The strategy was, because Vesta and Ceres were unexplored alien worlds, our real goal was literally to see what's there. This is, it's not like, it's not like when we go to Mars now, we've been studying Mars for many decades, right? We've mapped it in fabulous detail. We have spacecraft in orbit around Mars that can take images with a spatial resolution comparable to this. But I showed you the best picture we had of Vesta from the Hubble Space Telescope, and it wasn't a very good picture. It's a fuzzy blob. And Ceres, we didn't have pictures even that good. So our goal was to map these bodies. And by the way, Dawn is the only spacecraft ever to go to massive solar system destinations that were not previously visited by a flyby spacecraft. The first spacecraft that went to Mars that took pictures in the early 1960s, they flew by and just took some pictures. And then we had some more flybys that took some pictures. Venus, Jupiter, Saturn, Mercury, all these bodies. First, we flew by and took pictures. Dawn didn't do that. We went to these bodies and went into orbit and started by mapping. So the cool part is, as you're flying in, you're seeing things you've never seen before, but you know if the mission is successful, we're gonna get closer. We're gonna get closer. We're gonna get still cooler pictures. And so at first, we had just distant sort of fuzzy images. And the first orbits that we went to, if this is Dawn, if this is Vesta or Ceres here, we went into high altitude orbits, very high. So we could just kind of get the lay of the land, if you know what I mean. Preliminary reconnaissance. Then instead of being in an orbit real high like that, we took advantage of the ion propulsion system, which lets us maneuver a great deal, and flew down to a lower orbit. You can't see very well here, but an orbit like with this altitude, and mapped it again. And then we went to a still lower orbit and mapped it again. And so we kept getting better and better and better images, better and better pictures, sharper, clearer, more detailed, better spatial resolution. Of course, we were collecting many other kinds of data as well, spectra and things to learn about the chemical and mineralogical composition and other things I could tell you about. But each time we got closer, we could see more detail. And that was really our objective, to keep mapping it. We didn't know what we were going to find. And that's what's so cool. It's the discovery. When we go to Mars now, in fact, we're sending a rover to Mars, and just today's what, July 10th. So in 20 days, Perseverance rover and Ingenuity helicopter will go to Mars. But we already know in great detail what the landing site looks like. Sure, we want to get even closer and see more, but we're not going to have gross surprises like going to Vesta and Ceres did, where this is a whole world that you haven't seen before. Does that address your question?
Absolutely. This was really cool. Thank you.
Oh, good.
We have a question from Marinella, and she says, do you do any kind of maintenance to the spacecrafts? And if you do, how do you do it?
Well, we do all kinds of maintenance to the spacecraft. However, it doesn't involve people being at the spacecraft. So you, I'll just give you one example, but there are many. The ion engine, let me instead say the ion engine, is mounted to a gimbal so we can tip it and tilt it, right? So that we can change the direction it's pointing, okay? But that gimbal, I don't know if you know what a gimbal is, but it's a mechanical device, excuse me, it's got motors and things that move. Well, we operated Dawn for 11 years in deep space. Think of it, the extremes in temperature, radiation, vacuum. Mechanical devices don't necessarily like that. And so we maintain this gimbal by, and I'm going to give you the short version of it. It was more complicated than this. Every 60 days, we would by obviously remote control, have the gimbal, continue going over this way, move through its full range of motion in 2 axes to make sure that the lubricant in it was redistributed and that it had that preserved the capability, because much of the time we'd hold the ion engine in one direction and maybe just move it a little bit. But by moving the gimbal through its full range, we actually called that gimbal maintenance. It's the word that you asked, in order to make sure that this mechanical device would stay healthy for the duration of the mission. And there were many other things like that we did. Some were mechanical, some were electrical. And just like, of course, you also have to maintain software. And so we'd have to clean up files, and, we even upgraded the software during the mission, but that's sort of getting to different thing. Does that address the question?
Yeah, for sure. Thank you so much.
You are very welcome.
We will do 2 more questions because we have 3 books that Natalia is gonna raffle. So now that you have successfully mapped Vesta and Ceres, what is the future of these 2 bodies?
Good question. Again, all these are good questions. NASA right now is studying a mission to go back to Ceres. And it would involve, so this is, I should say, this is just a study, and studying it does not mean NASA's going to do it. The way I think of it is the universe is full of exciting destinations and exciting things to study. And while NASA has a lot of money, it's finite, not infinite amount of money. We can't do everything, right? So NASA has very well-developed processes to carefully decide how to spend its money. If we had an infinite amount of money, we'd have spacecraft all over the universe. Well, we don't. Part of it is assessing how feasible these missions are. Okay, so that's just a little aside because I don't want you to think the fact that we're studying it means we're definitely going to do it. But there are some people studying a mission that could land on Ceres, perhaps drill down into the ground, collect a sample, and maybe launch back up off Ceres and bring it back to our planet. So it takes a lot of work to study these things to decide whether they're feasible or not, but that's going on. There have also been studies of sending a rover to Vesta. So I don't know yet what the future is, but both bodies are so interesting. I have no doubt there will be subsequent missions to them. And maybe some of you, maybe even the person that asked the question, will get to work on one of those sometime.
That would be amazing.
If you do, send me an email and let me know.
Oh. You can send us your email after this so they can send you their emails. That would be great.
Okay.
So you said it's very emotional to experience the launch of a satellite you sent building for years. It is true that you always make at least 2 copies?
Oh, no, not at all. In fact, in general, we do not. They're too complicated and too expensive. So for most spacecraft, you build one. And most rockets succeed, but if the rocket blows up, you're out of luck. I should tell you, it's not the most emotional part of a mission, but it's one very visible, scary part.
Okay, I think the last question would be, I noticed that there was no boosting before, during, and immediately after the gravity assist around Mars. Can you explain a little more about gravity assist and why not extra propulsion was necessary for the maneuver? Thanks. Would thrusting only have upset the trajectory?
Okay, that is a much more complicated question than it's a very good question. The answer is much more complicated than the person who posed it might have thought. So let me just tell you that sometimes thrusting with the ion propulsion system during the gravity assist is beneficial. Sometimes it's not. So there's no general rule about whether you should or shouldn't. For quite complex mathematical reasons in optimal control theory, if you are familiar with that, it turned out on dawn not to be beneficial to thrust as we flew by Mars. However, there are other trajectories to other solar system bodies with other details. I mean, there's Avogadro's number of differences between all these different missions. Sometimes it works out to be beneficial, sometimes it doesn't. We have extremely sophisticated software that uses very complex mathematical principles to tell us when it makes sense to thrust. I shouldn't say makes sense, when it is mathematically optimal to thrust, and when it is actually mathematically optimal not to thrust. There are times where it is preferable not to thrust. It turned out for Dawn's trajectory, given the myriad parameters that we had, to go from Earth past Mars to get to Vesta, it was mathematically optimal not to thrust there. It's more complicated even than that, but I know we're running out of time, so can I get away with that answer?
Yeah, all good. Thank you. Thank
Okay.
you. I appreciate it.
Marc, I'm really sure like you just made our heads blow and our imagination, it's like out of this world right now. And also our hearts are really warm with all your advice and everything you've showed us today. So I think we are so thankful for it. And now let's go with Natalia and Bruce.
Well, one final one, Marc, something about the statistic about how many meteorites on Earth are from Vesta. Was there some interesting fun fact about that?
There is, and I didn't get into it here just because I didn't want to take too much time, although I'm actually sitting in a room here where just around behind this, I've actually got a piece of Vesta. I can get it if you want me to, but, but maybe Bruce is going to do it.
Yeah, I found this. I wasn't sure, but could that have come from Vesta originally?
It's pretty unlikely. Should I actually get my piece?
Sure, if you can, that'd be great.
Okay. Got a little bit of a tight spot here. I will be right back.
We're going to see a piece of Vesta. It's really worth it.
So can you hear me even while I'm walking around?
Yeah, we can hear
Can
you.
hear you.
Okay. Okay, I'm back. So I'll just take a moment to tell you, I told you about this big impact at Vesta, right? 1 billion years ago, I showed you all the stuff sprayed out and it landed back on. But the impact was so powerful that some of the material escaped from Vesta, right? It was given enough energy to achieve escape velocity, and some of those rocks made their way to the part of the solar system where you and I live. And one of them landed in this box. And I will hold up, there's a strong reflection, and I apologize for that, but can you, there. This is a slice of a rock. Here's my finger for scale. So, Bruce, you're going to take a picture? Go ahead.
Sure.
So this was a rock that fell in Western Australia, and it was found in 1984. I mean, I don't know when it fell, but thanks to Dawn's spectroscopic analysis of Vesta and laboratory spectroscopic analysis of meteorites like this, we know that this came from Vesta. Now, let me get to the specific cool thing. Well, that's already cool. The specific cool thing that Bruce was referring to. Maybe some of you have heard we have meteorites from Mars. Do people know that? And maybe you even know we have some meteorites from the moon. But Mars, the moon, and Vesta are the only solar system bodies to which we have linked specific meteorites. And although Vesta is much, much farther away even than Mars, we have more meteorites from Vesta than we have from the moon or Mars. So we now know that approximately 6%, think of this, 1 in every 16 meteorites seen to fall to Earth came from Vesta. And so the reason I have this is they're very common. I didn't buy this because of my work on Dawn. I actually bought this before I worked on Dawn. I've been a space enthusiast my whole life. I thought, boy, I'd really love to have a meteorite. This was pretty inexpensive. It didn't occur to me when I bought it that I would end up being responsible for the mission that would determine that this kind of rock, this rock, came from that destination. They're so common. If you've seen meteorites in a museum, there's a good chance, again, 1 in 16 seen to fall to Earth, 6%. There's a good chance you've seen one that came from Vesta. I'll tell you one more cool thing, along with my apology for giving these long answers. I told you that we have more meteorites from Vesta than from the moon or Mars. We actually have more material from Vesta than we have even from the moon, even accounting for the hundreds of kilograms of material Apollo astronauts brought back. We have multiple metric tons of material from Vesta that we know is from Vesta thanks to Dawn. So there you go.
That was amazing, amazing. We need to take a biology probe to Vesta. I'm sure there will be cool stuff there.
Well, I hope one of you gets to be involved in it.
I hope. Natalia, I think it's your turn.
Okay, thank you so much, Dr. Rayman, for giving us such amazing experience with this video conference. As a final activity, Bruce gave us some ebooks to raffle today between the attendees. So I'm just gonna share my screen so everybody can see how we raffle the ebooks. So here we have the names of every participant. They are written as the way they appear on the Zoom. So that's why some of them have their last name and some of theirs don't. But yeah, first of all, we're gonna raffle an ebook of the book La Ciudad, Espacio Colectivo, Intereses Privados, written by David Porras Alfaro y Julio Viunesa Ancud. So I'm gonna click here just to see who wins. So Ivani Calvo won the ebook, and if you can send us your email through the chat, it would be really useful so we can send you the code.
Yeah, I think Ivani may not be here now. She's the director of the planetarium here, incidentally, Marc. But I think she had to leave a little bit early.
Okay, so yeah, we can contact her after this.
Or if she's not available, just give the book to me.
Okay, I mean, like, that was fair.
We can send you one.
No, I'm just kidding. I'm just kidding.
We're gonna mix the names again, and this time we're gonna raffle a book called Las Matemáticas de lo Cotidiano, and it is a book of math. So, and the winner is Valeria Campos. As well, Valeria Campos, we're gonna send you an email. We will send you the code for it. And the last one is a ebook of Costa Rica en la NASA, written by Bruce. So yeah, like,
and Ana Luisa.
And Annalise, yes, of course. Yeah, right. And we're gonna see who's the winner. And Andrea Solano. So we're gonna, okay, if you're connected still, send us your email through the chat. And if you're not, we're gonna look in the people who subscribe to the talk. And
Thanks so much to Editorial Tecnológico. That's the Costa Rican Institute of Technology Press, University Press, for giving us these books and for publishing our book. We hope to do a sequel of other Costa Ricans working in the space industry, and we'll have some details about that in the next month or so.
Mm-hmm. So thank you so much, Dr. Rayman, again. Just a quick notice for women who are interested in data engineering or data analysis. We, as SOAS Costa Rica, are working on a program of mentoring with McKinsey & Company. So if you want more information about the program, you can just go through our social media and go through the links to it. And yeah, again, thank you so much, Dr. Rayman, and
Thanks to all of you. I appreciate your setting this up. And thanks to everybody who joined so I could share my excitement with you. And good luck to all of you.
thank you. Have
Thanks
a
a
good
lot.
night.
See you.
Bye.
Thank you.
Bye.